Alright, so let's look at our next theorem, Theorem 2.3.4. Now this theorem, again, now we've reached a point where we can now establish the answer to our question, which is, does the determinant distribute in general over a product of matrices? And the answer is yes. Theorem 2.3.4 states that if A and B are n by n matrices, then the determinant of A times B is the product of the determinants. Okay, so we're going to prove this in the next little clip. Alright, so let's see why it is the case that the determinant distributes over the product between matrices. So we have this, recall the following theorem. This is a theorem from section 2.1 and 2.2. This theorem states the following. So if A and B are square n by n matrices, then the product between the two is invertible if and only if A is invertible and B is invertible. Right. So we can prove this as follows. We can prove it. We first assume that that A times B is invertible. Okay, now if A times B is invertible, then we can apply the equivalence theorem. Now I want you to go back in your notes to the points raised in the equivalence theorem. So we're going to apply it in this case. So we're going to prove by contradiction. So we want to prove that A is invertible and B is invertible. So let us assume that B is not invertible. Right, now go back to the equivalence theorem. What does it mean for B to not be invertible? By the equivalence theorem, this expression here has a non-trivial solution. Remember, the equivalence theorem says that if a matrix is invertible, that is mathematically equivalent to saying that, say a matrix A is invertible. That's equivalent to saying that the expression AX equals 0 has only the trivial solution, right? So if B is not invertible, it means this expression here has somewhere a non-trivial solution. And let's say C is a non-trivial solution, and that's not the zero matrix. Okay. Then let us consider the product between A and B, and let us look at this product here. Then that is because of associativity, we can group B and C together. All right, and what does that become? That becomes A times the zero matrix. And remember, this is true. Why is that true? Because BC is that. Remember, C is a non-trivial solution to this equation here. So if I plug that C in the X there, that is going to be the zero matrix, right? And A times the zero matrix is a zero matrix. It follows that from here, it follows that this matrix A times B, that expression, it follows that this expression has a non-trivial solution. A non-trivial solution being in this case the vector C. Because if I plug C bar in there, it gives me equality. Now, this contradicts the equivalence theorem. Why? Why does it contradict the equivalence theorem? Why does it contradict the equivalence theorem? Because we assume that A times B is invertible, and by the equivalence theorem, because this is invertible, this system here will have only the trivial solution, and in this case it's got a non-trivial solution here. So that contradicts the equivalence theorem. Hence, Bx equals 0 only has the trivial solution. It only has the trivial solution. So we can say, we can therefore say that B must be invertible. Because you're getting a contradiction here. That will contradict the equivalence theorem, so therefore that's going to force B to be invertible. So we know that B is invertible, so now we just need to show that A is invertible. Right, so we know that A times B is invertible. Okay, so as A times B is invertible, there exists, so there exists a matrix C such that C is B's inverse, the identity matrix, okay? And also, we also know that that must also hold. Okay, so because A times B is invertible, it has an inverse C, and C is also going to be invertible because C's inverse is A times B. Okay, right, so now we just need to show that A is invertible. Okay, from this equation here, it follows that, right, so we know that A times B times C is the identity matrix, which is going to imply that A times B is going to be C's inverse. And I'm allowed to write this because C's inverse exists, because the inverse of C is A times B. So I'm allowed to write that. And from there we can then again apply the same law, the same rules there, and therefore deduce that A is C's inverse times B's inverse. All right, and therefore A is simply BC's inverse. Okay, right, so hence A times, A is invertible, because B times C is invertible. remember, there's a theorem that states that if B and C are both invertible matrices, then the product between those two matrices is also going to be invertible. Okay, so therefore because B and C are both invertible matrices, it means that their product is also going to be invertible. And the inverse of an inverse is also invertible. Okay, so we proved that if A times B is invertible, then A is invertible and B is invertible. So now we just need to show that if A and B are invertible, then A times B is invertible. But this is true because it follows from a theorem in chapter 1. So now what we do is we assume that A and B are invertible. Okay, then because A and B are invertible, that theorem states that A times B's inverse is going to be B's inverse times A's inverse. Thus, A times B is invertible. All right. Okay, so therefore if the product of two matrices is invertible, then both the matrices in the product will be invertible. So now we move on to the next theorem, which tells us the following. Remember, we said that we wanted to check why the determinant distributes over the product. Okay, so
again, if we take two square matrices, then the determinant of the product is equal to the product of the determinants. Okay, so let's quickly look at the proof here. Again, application of everything we've
done up until now in section 2.3. Right, so we have to look at two cases. The first case, let us assume first that A times B is not invertible. Now, we said previously that if a square matrix is not invertible, it means that its determinant is definitely going to be 0. Right. Okay, that follows from the previous theorem we did. It follows that the determinant of the product between A and B is going to be 0. Okay. Now, if we look at our previous theorem, these two statements, A, B is invertible, is equivalent to the statement A is invertible and B is invertible. So that means you cannot have one without the other. If one of A and B is not invertible, then A times B is not going to be invertible. And if A times B is not invertible, it's going to mean that at least one of the matrices A and B is not going to be invertible. All right, so basically applying that, this implies what? This implies by our previous theorem that the determinant of A is either 0 or the determinant of B is 0. All right, remember, a matrix is invertible if and only if its determinant is not 0 by the previous theorem. So therefore, if A is not invertible, its determinant is 0, and if B is not invertible, its determinant is 0. So hence, what do we have? We have the determinant of A times B. We said that's 0. Okay? So therefore, you can write that as 0 times the determinant of B. Okay, and that we can say then is the determinant of A times the determinant of B. Now, I didn't write it down here, but we can assume, because either the determinant of A is 0 or the determinant of B is 0, we can assume without loss of generality that the determinant of A is 0. Okay, so you can replace 0 with the determinant of A.
So our theorem holds, okay? So our theorem holds. So now we need to consider the second case, and that is where A times B is
invertible. So assume A times B is invertible. Now, by our previous theorem, because the product is invertible, it means that both A and B are invertible. Okay, so hence A is invertible. A is invertible. A is definitely invertible, and by the equivalence theorem, A is a product of elementary matrices. So by our equivalence theorem, A is a product of elementary matrices, where EI is an elementary matrix for all indices between 1 and R. Okay, so thus
the determinant of A times B is the same as the determinant of the product of elementary matrices, right, multiplied by
multiplied, that I should just leave that out and place the B there. Sorry about that. Okay, and using our previous distribution theorem, that then becomes the determinant of E1 multiplied by the determinant of B2 up until the determinant of ER. Okay, multiplied by the determinant of B. Okay, and again, applying our previous law, these are all, that should be an E. Using our distribution law again over elementary matrices, that is just then the product of these elementary matrices. Okay. Okay, and that is the determinant of A multiplied by the determinant of B. Okay, so that takes care of our theorem. So therefore, the determinant always distributes over the product between matrices. And in fact, if you can have more than 2 matrices in your product, the determinant is still going to distribute in exactly the same way as it did over elementary matrices. Right, that brings us to Theorem 5, which states that if A is an invertible matrix, then we can easily find the determinant of the inverse of A by simply calculating the determinant of A and looking at 1 over the determinant of A. Now this is easy, it's easy to prove this. It's a simple application of Theorem 2.3.4. Right, so let's check why that inverse of a matrix, why the determinant of the inverse is 1 over the determinant of the matrix itself.
So this is a very easy result to derive. So let A be an n by n matrix, invertible matrix, an n by n invertible matrix. Then the determinant of the inverse is 1 over the determinant of A. And the way we do this is very simple. And this is also again a sort of a nice little exercise to do to
apply our theorems we've done up until now. So all you do is essentially, because A is invertible, we know that if we multiply the matrix A inverse with A, that'll give us the identity matrix. Okay, So therefore, applying the determinant on both sides, using our identity, that matrix identity, we have this, and that we know the determinant of the product is the product of the determinants. So that's going to be the determinant of the matrix A inverse multiplied by the determinant of A. And what's the determinant of an identity matrix? An identity matrix is pretty much an upper triangular matrix, and that we know the determinant is the product of the entries on the diagonal, which in this case is 1. Okay? And from there you can then solve the determinant of A's inverse as 1 over the determinant of A. Alright, so that is very straightforward. Alright, so let's look at some applications of the matrix identities, the determinant identities that we've done up until now. So let's say you have two matrices A and B that are n by n, and the one has determinant 3 and the other one has determinant minus 2. Then if we look at the first problem, the determinant of the product of A and B is the same as the determinant of A times the determinant of B, and that then leads to 3 times minus 2, which is minus 6. Alright, let's look at the second problem. Again, you apply the fact that the determinant distributes over the product. There we've got the determinant of A squared, and that then becomes the determinant of the matrix A multiplied by A, and the determinant distributes over that product into determinant of A multiplied by determinant of A, and that becomes 3 times 3, which is 9. Alright, let's look at problem number 3. That's the determinant of B's inverse multiplied by A. Remember that the determinant of B's inverse is 1 divided by the determinant of B. So that determinant of B's inverse times A becomes the determinant of B's inverse multiplied by the determinant of A. And the determinant of B's inverse is 1 over the determinant of B, which is 1 over minus 2, multiplied by the determinant of A, which in this case is 3. So we end up with minus 3 over 2. Alright, so the next problem, problem number 4, is the determinant of 2 times the matrix A. Here we apply the first identity we did in section 2.3. Remember, we proved it by induction. In this case, the determinant of 2 times A is 2 to the power of n. Remember where n is the number of rows and columns of the matrix A. And that we multiply that with the determinant of A. So that becomes 3 times 2 to the power of n. Alright, let's look at problem number 5. That's again an application of the same identity used in problem 4. That becomes the determinant of 3 times B's transpose becomes 3 to the power of n multiplied by the determinant of B's transpose. And we know that the determinant of B's transpose is the same as the determinant of B. And you can actually prove that, again, that identity using this similar type of inductive argument we used in the beginning of this section. That first proof we did. So that becomes the determinant of B's transpose multiplied by 3 to the power of n, which is 3 to the power of n multiplied by the determinant of B, which in this case is minus 2. So it's 3 to the power of n times minus 2. Right, last problem is the determinant of A multiplied by A's transpose. Remember that the determinant of A's transpose is the same as the determinant of A. So the determinant of A times A's transpose is the determinant of A times the determinant of A's transpose. And the determinant of A is 3, and the determinant of A's transpose is the same as the determinant of A, which is in this case 3 as well. So that gives us 3 times 3, which is 9. Alright, that brings us to the adjoint of a matrix. So what is the adjoint of a matrix? Or it's also called the adjugate. So it's simply, it's denoted by ADJ of A, and it is simply the transpose of the matrix of cofactors of A. So what you do is you take the matrix A and you work out the cofactor for each entry in that matrix. And then you form a matrix where the entries are the cofactors that you worked out, and then you take the transpose of this matrix, and that is the adjoint. And it turns out that we can use the adjoint to compute the inverse of a matrix. So this is a different way of computing the inverse. So if A is an invertible n by n matrix, then the inverse of this matrix is given by the adjoint of A multiplied by a scalar, and this scalar is 1 divided by the determinant of A. Okay, so let's look at the derivation of Theorem 6. Okay, so let's look at the derivation of the adjoint formula for the inverse of a matrix. But before we actually delve into this, I want to illustrate a particular property that holds. For simplicity's sake, let's take a 3 by 3 matrix.
A21, A22. Okay, now
what I'm doing is I'm claiming the following. Let's look at, as an example, let's take the third row's cofactors. So let's look at the third row's cofactors. So that is cofactor 3,1, cofactor 3,2, and cofactor 3,3. And let's, for argument's sake, multiply that with the first row. And let's see what happens here. Well, it turns out that this is in fact 0. And why is this the case? Okay, why is this the case? So if we look at the following. So let's define this new matrix A prime. It's still the old matrix, but the only difference is what we do is we delete the third row. And we replace it with the first row. Okay, now using this matrix here, I want you to note that the cofactor of this matrix A prime of the entry in the third row in the first column. And remember, this is the sign minus 1 to the power of 3 plus 1 multiplied by the minor of the entry of this entry in the third row in the first column. Okay, and the minor, remember, is the determinant of the matrix that I get by cancelling the third row in the first column. So if I take the third row in the first column, if I cancel the third row in the first column, that is the same as cancelling the first row in the third column of the matrix A. And that, again, that will, therefore, these two cofactors will be the same. This is the cofactor of the entry in the third row in the first column of the matrix A. And you also have that this is also true. Okay, and we also have that is also true. Okay, so the cofactor of the entry in the third row and the second column, which now pretty much you're going to have to calculate the determinant of this matrix here, if I cancel the third row and the second column, and that is again going to be the same cofactor that I get there by cancelling the third row and the second column, and so on and so forth. Okay, for C33 as well. Now, so let's look at the determinant. Let's look at the determinant of A prime. The determinant of A prime is 0 because you've got two rows that are the same. Remember, section 2.2 says that if one row of a matrix is a scalar multiple of the other row, then it simply means that the determinant of that matrix will be 0. because you can take a multiple, you can take -1 in the third row and add that to the first row, and the determinant of the new matrix will be the same as the determinant of the old matrix, which in this case is 0. So but the determinant of this matrix A prime can also be written in a different way. If we expand along the third row, so if we look at the cofactor expansion along the third row, so then we keep pretty much, what do we do? That is going to be the entry in the third row in the jth column of this matrix A prime multiplied by the cofactor of the entry in the third row in the jth column. And j is going to run from 1 up until 3. Okay, now if we go and work that out, that is simply A31 C31 plus A32 C32 plus A33 C33. Okay, and again we can use these quantities here and replace, and therefore we get A31 prime C31 plus A32 C32 plus A33 C33. And what's the entry in the third row in the first column of matrix A prime? That is simply going to be A11 C31 plus A12 C32 plus A13 C33. All right, now this quantity here is exactly that quantity there, which is what I want. So this quantity here is equal to 0. Okay, so what is the moral of the story? We can take this argument and apply it to n by n matrices in general. So what it says that if I take the ith row of a matrix and I multiply that with the cofactors of a different row, then that's always going to be 0, and you're going to just use the exact same argument. Okay, so we are ready now to verify that result we spoke about. Okay, so again, what we're claiming here, we're claiming that the matrix A multiplied by the adjoint of A can be given as the determinant of A multiplied by the identity matrix. Now you can see here that you can then you can go and solve for the inverse of A as the adjoint of A multiplied by 1 over the determinant of A. Okay, so to do this now is not terribly complicated, because now remember what we did here just above. We can use that now to our advantage. So again, note that you could take A and multiply that with the adjoint of A. And what does that look like? So if we take a general matrix A, okay, so that is, so what is the, if we look at this product, so what does the entry in the ith row and the jth column look like? So if you look at this matrix here, okay, and you look at the entry in the ith row and the jth column. So again, that is going to be the ith row multiplied by the jth column. So that is going to be the ith row Okay, so the entry in the ith row in the jth column then becomes this general expression. Okay, so that's the entry in the ith row in the jth column. So what happens if the indices I is equal to j? In other words, we're looking at entries on the diagonal. So if I is equal to j, then this entry in the ith row and the ith column is going to be this entry here. Okay, and what happens if I is not equal to j? Now we are going to apply our previous argument, and that is going to imply that you have the following. Now see what's happening here. Okay, so we've got cofactors that we multiply. We have a row, the ith row, and we're multiplying this ith row with cofactors from a different row. And remember, by the previous argument, that's always 0. That's always 0. And it's 0 because of the fact that that a row multiplied is always 0. Okay, so therefore okay, so why does this matrix become this matrix here? Well, now we've got the entry in the ith row in the j's column where I is not equal to j. Those are all 0. And the entry in the ith row in the j's column where the ith row in the index column is equal to the index row is going to be this expansion here. Now, what exactly is this? What exactly is this? This is going to be the determinant. This is going to be the determinant of A. This is going to be the determinant of A. Okay. Okay, so this becomes the determinant of A multiplied by the identity matrix. All right, and that concludes our claim. So by our claim, okay, so that is the derivation of the adjoint formula for the inverse. All right, so next we look at the procedure for inverting a matrix using the adjoint method. So you first start off by, you compute the minor matrix M consisting of the minors of each element. So for each element you take the entry in the ith row in the j's column, and what is the minor of the entry in the ith row in the j's column? It's the determinant of the matrix that I get by cancelling the ith row in the j's column of the original matrix and then determining the determinant of that matrix. Then what you do is, once you've done that, then you introduce the sign. Remember, because you're determining the cofactors. So of each minor entry, you determine the sign. So for the entry in the ith row in the j's column, it's minus 1 to the power of I plus j. That's the sign. So you take the matrix, you constructed M, and then you construct C by introducing the sign for each value. Then you compute the determinant of the matrix A, and all those things you throw together, and you pretty much calculate the adjoint of A, which is the matrix you obtained from part 2, and you take the transpose of that, and then simply it's a question of substitution, substituting it into your formula, and then getting the inverse of A. Alright, so we are going to just quickly do an example here. I want you to do the second example as an exercise on your own. I'm going to do the first example. Alright, so let's start off by calculating the inverse of the matrix A using the adjoint method. We follow the procedure described previously. So we are going to calculate first the entries of the matrix M. Okay, so I'm going to calculate two entries of the minor matrix, and I'm going to first calculate the entry in the first row in the first column. Okay, so what is the entry in the first row in the first column of M? It's given by M subscript 1, 1, which is given as follows. It's the matrix A that I take and I cancel the first row and the first column. Then I take the determinant of this resulting matrix. I indicated it with the black lines on both sides, the determinant of that matrix. Alright, so let's calculate another entry. So I'm going to calculate the entry in M that lies in the third row in the second column. And this entry is given by M subscript 3, 2. How do I get it? Take the matrix A, cancel the third row in the second column, and take the determinant of that resulting matrix. And that can be easily calculated as 1 times 4 minus 1 times 2, which is 6. Alright, so let's move on to calculating the matrix C. The matrix C is now the matrix comprising of the cofactors. So we start off by calculating the entry in the first row and the first column. That's given by C11, which is minus 1 squared times M11, which you already calculated, and that's minus 18. Now I'm also going to just calculate another entry of C, which is the entry in the third row in the second column. And this entry again is given by C32, which is minus 1 to the power of 5 times M32, which we already calculated. And that is simply minus 1 times 6, which is minus 6. Okay, so then we calculate the determinant of A. We already calculated all our cofactors, so we can find the expansion of A along the first row and work out the determinant, which happens to be minus 2. Now that we have that, we can go and calculate the adjoint of A, which is taking the matrix C and working out its transpose, and then substituting that into our adjoint formula. So it's the adjoint matrix of A multiplied by 1 over the determinant of A. So we're going to multiply it with 1 over minus 2. Alright, this brings us to Cramer's rule. So just a quick definition. If you have an n by n matrix and an n by 1 column vector B, then A subscript j is simply the matrix that we form by taking A and deleting the j's column, and then placing in the j's column the vector B. And there's mathematically how A subscript j is defined. that's the notation we will be using. So looking at the example, you take A and the vector B. A1, you cancel the first column of A and replace that with the vector B. A2 the same, you delete the second column and replace it with B. And A3, you delete the third column and replace it with the vector B.